So for this video, what I'm going to do is I'm going to talk about reaction mechanisms, which although it's the last topic of the chapter, and there aren't real calculations to do in this, this is a pretty intensive calculation-based course. In a sense, this is one of the most important topics, and it's something that for those of you that go on to organic chemistry will spend an enormous amount of time considering, which is what's actually happening at the molecular level when a chemical reaction takes place. And this is a big area of chemistry, which is to figure out what's happening at the molecular level. Thus far in section 1, when we talked about average rates and instantaneous rates, we were looking at things from the macroscopic perspective. Changes of concentration. Remember, if the concentration changes by 10 to the minus 10 molar, tiny number, right? That's still 10 to the 13th molecules per liter, right? So if reaction rates are in molar, then we're really talking about very large numbers, and rate constants were per molar per second, right? So we're really still talking about large numbers of things. What we're going to look at in this section is the detail of just like one molecule reacting with one molecule. Can we analyze it from that perspective? And mainly what we're going to do is we're just going to introduce the terms to you. Again, if you go on to take organic chemistry, that's where you really look at what's happening for specific reactions. We're just going to give you some terminology here, a way to sort of look at the equation and make sense of it. And we won't do, particularly real complicated experiments for this. So let me show you a reaction here. Okay. All right. This is good. So this is a nice little intro here. The terminology we're going to use is molecular or molecularity, I think is the term. Okay. So identifying the molecularity of an elementary reaction. Identify the molecularity of each elementary reaction in the table below. So the terms that we're using here, unimolecular, cool word, right? Bimolecular, termolecular, quadrimolecular. These mean 1, 2, 3, 4. That's all it means. Uni is 1, a unicycle has 1 wheel, a bicycle has 2, a tricycle has 3. But we don't call them trimolecular. Interestingly enough, we call them termolecular. Right? A quadruped is an animal that runs on 4 legs, right? So that's 4. So 1, 2, 3, 4. Now, really what we're doing here in the elementary reaction is we're saying that suppose you have this reaction occurring, you don't know exactly what's happening in it. You can look at the reactants and the products, and you can study how fast the reaction is going, measure the rate constant, get the molecularity out of it, all of that. This is an individual step we're looking at. An individual step in a reaction is called an elementary. Elementary means kind of simple. It's the simplest part of the reaction that's taking place. So the thing about elementary reactions is that we often don't know what they are. We have to kind of like propose what they are and then do experiments to figure out if they are. But we often don't know what these individual little reactions. So for example, if I take something as simple as hydrogen plus oxygen forms water, that looks so simple, H2O, right? Turns out it's not a simple thing. There's all kinds of reactions that are occurring to form the water out of the H2 and the O2. So, the elementary step is just, or elementary reaction is just the simplest kind of look at what the molecules are doing. So these are proposed elementary reactions here. The first one says that 2 molecules, so notice I'm saying molecules and not moles. These are just individual particles. 2 molecules of N2O5 are colliding with each other. And when they collide with each other, they reform as 2 molecules of N2O4 and 1 molecule of O2. All this is saying is these 2 molecules collide, an O2 comes off, okay? And 2 N2O4s come off. So the nice thing about this particular question is very simple. You just count how many molecules you have on the reactant side. That's all you got to do. There's 2 molecules here, so that's bi. So you would pick bimolecular, okay? Let's look at the second one. This is saying that at the simplest level, 1 molecule of N2O is breaking up into 2 molecules of N2 and O. It's actually a molecule in an atom, but we often call them molecules, even if they're just individual atoms, so that we don't have to say molecules and atoms every time. One molecule, right? It's just one, is breaking up into N2 and O. Okay, that's all that's happening. So again, just look at the coefficient. It's a 1, so it's unimolecular. This one, two molecules, but look here, don't forget, there's a Br2 as a reactant too. So there's 2 molecules here and 1 molecule there. That's a total of 3 molecules. There's actually 3 molecules colliding. Now this is actually, it turns out, a very slow process. The probability that 3 molecules are going to collide at the same time isn't very high. So it's a pretty slow process. Bimolecular, unimolecular are much faster generally. And so most reactions that you look at are usually uni or bimolecular. Termolecular. Termolecular is less common. It can happen, but it's less common. So 1, 2, 3, termolecular. Okay. I just want to quickly see if there's any others that are any really different. Sometimes they might give you one that's very different. 1 molecule, so that's bi. 2 molecule, okay, yeah, it's all the same, right? Unit, bi, or ter. You're not going to see quadrimolecular very often. I'm not going to claim it's never going to be there, but it's pretty rare. Okay, so let's take a look at another one. It's actually a fun section, but we don't really spend too much time on it, but go over this. It's kind of cool, especially if you're going to take organic. You're going to hear these terms in organic chemistry like SN1 or SN2, or maybe you have friends that are taking organic chemistry, which means substitution nucleophilic unimolecular, SN1, substitution nucleophilic SN2 bimolecular. Bimolecular means 2 molecules are reacting. Unimolecular means that one is just falling apart usually. Okay, so consider the following mechanism. Now this is called a mechanism. A mechanism is a set of elementary steps. Typically it's more than 1 step, 2 or 3 steps. Could be more even, but this is, in general chemistry, we give you 2-step processes. We're not going to give you 3 or 4, but generally it's 2 for this type of course. Consider the following mechanism for the decomposition of N2O. Okay, so this is N2O, I'm sorry, NO2, nitrogen dioxide. It's decomposing, breaking up into something else, okay? What this is saying is that it happens in 2 individual steps. The first is NO2 breaks up into NO plus O. So think about that. That's pretty simple, right? 2 oxygens on a nitrogen, one of them knocks off. So the molecules are colliding, oxygen pops off. Now you have an NO and a separate O. Second step, that O, that oxygen that we formed in the first step, it starts moving around in there and it finds another NO2 to collide with. And it collides with that NO2 to form an O2 and an NO. So this is like an exchange. The O is taking the nitrogen oxygen off of the other oxygens, okay? So that you get NO and O2. I'm sorry, the oxygen is pulling an oxygen off the NO2 to form O2 and leaving the nitrogen with only 1 oxygen, okay? You can draw little pictures for yourself here. Maybe I'll do it for this one just to show you. Write the chemical equation of the overall reaction. Are there any intermediates in there? And if there are intermediates, write the formula down, okay? So let me show you this one. These are kind of fun to do. So often we number them. They don't do it here. This is NO2. I'm not going to put the states of matter because it's not important. I mean, these are all gas phase anyways. And I'm actually going to put in here, they don't do it. I'm going to put K1 to indicate there's a rate constant for that process. And the rate of this step, this is called a elementary step, is K1 times NO2 to the first power, because there's only a 1 there. So for elementary reactions or mechanisms, the elementary steps, you just look at the molecularity. If it's unimolecular, that means it's a 1 there. Okay. Now, that's our first step. We have a second step. What this is saying is that the oxygen that we formed here is now colliding with another NO2. There's a bunch of NO2s in there, right? And it's forming O2. This, I guess you might call this it's abstracting. I think that's the word we use. It's abstracting an oxygen from the NO2, pulling off an oxygen. This would be K2. And the rate for this reaction would be K2 times O, right? Times NO2. So for elementary reactions, and these are elementary steps here, together we call that a mechanism. The mechanism is the combination of the elementary steps, like we just looked at a moment ago. Each one is going to have its own rate constant, and each step is going to have its own rate law. So here's the rate law for the first step. Here's the rate law for the second step. We can write it merely from the balanced equation. Okay. Now the question is, what's the overall equation? You actually learned how to do this back in Chem 11. You combine equations. If you combine equations, everything that's a reactant you put together is a reactant. Everything that's a product you put together. So the reactants are NO2, O, and NO2. The products are NO, O, O2, and NO. Then you combine anything that's the same term. See, that's NO2? So you have 2 NO2. And then you have an O. And that's going to give you an NO and another NO. So 2 NO, an O, and an O2. However, you can also cancel things, right? If you have O on both sides, you can cancel them. So we're left with 2 NO2. Now I'm going to put the states of matter in, because when you enter this, it will probably want the states of matter. And there you go. Okay. Now, that's the overall equation. Okay. So anything that's a reactant, you put together. Anything that's a product, you put together. You combine like terms, and you cancel anything that's on both sides. Now, here is our definition of the intermediate. An intermediate is formed in one step and then used in the next step. Okay, so you see how the O is formed here in the first step, but then it's used in the second step. That's what makes it an intermediate. Okay, now when you write the overall equation, the intermediate will be missing from the overall equation because you're canceling it, right? The intermediate generally gets canceled when you combine these elementary steps, right? Remember, so each one of these is called an elementary step. And then you add them, and that gives you the overall mechanism. Okay, so the elementary steps together are the mechanism, and combining them, when you actually go through adding them together, you get the overall reaction as well. Okay. So there we go. So if there's more than one, it says to put a comma and then put the formula. Okay. But for this one, yeah, the answer is yes, there is one. Okay. Let me show you one more. Actually, I may not show another one because these are pretty simple. Oh, well, here's one with 3. So I'll show you this one. I'm sorry, I didn't realize there were 3. So that's cool. Sometimes when the problem's more interesting to me, I'm going to do it just because I'm interested in it. Okay, so here you have 3 steps. Okay, and same issue though. You know, what's the overall equation? Are there any intermediates? If there are, you can kind of look at it and see if there's intermediates, right? Here O is formed. Here it gets used up. That's an intermediate. NO3 is formed here. Oh, NO3 is used over there. That's going to be an intermediate 2. Okay, so let's go through it. Okay, so we got O3. Let me turn this around a little bit. I'm sorry. Let me turn this around. So we got O3 plus NO. So this is the first step in this mechanism. So I'm going to say, you know, R1 equals K1 times O3 to the first power times NO to the first power. It's not asking you to do this. I'm writing the rate laws for each step, but the reason I'm doing that right now is because in the next kind of problem, you need to be able to do that. It's going to ask you to do that. So I'm doing it early for you. Second step, O plus O3 gives you 2O2. K2 times O times O3, right? First power. So, you know, first step, bimolecular, right? Because you've got, what you do is you add all the coefficients of the reactant side. So in the first step, you've got a 1 and a 1 for the two reactants. 1 plus 1 is 2. That's bimolecular. For the second one, 1 plus 1 is 2, bimolecular. So this one's also bimolecular. Okay, now we got a third step. By the way, some mechanisms have like 10 steps. We're not going to do those ones. R3 is K3 times NO3. And I just want to remind you when you, and this is 2 again, so it's bimolecular. When you're doing those original problems way back at the beginning, you know, rate laws, R equals K times concentration of A times concentration of B. You can't just look at the coefficients to find the rate law there. You have to go through experiments and figure them out. But if it's an elementary step, which is something you're proposing, then you can, okay? And the reason you can't do it for the overall rate law is because it's going to be a mechanism. Reactions generally are mechanisms. They're multiple steps. So you don't know what the relationship between the coefficients and the exponents are in the rate law because there's multiple steps. So we don't know which steps are important, you know, to the degree that they are, okay? So again, what's the overall, and then are there any intermediates? If there are, write down what they are. You know, I'm going to do this already. We do this in Chem 11. Anything that's the same on both sides, you can cancel. Okay. So NO3 is going to cancel. I'm going to cancel them first. That just saves some space and time. And then I'm going to note that there's 2 of these. And there's 2 of those. So I can just go straight to 2O3 gas plus 2NO gas is going to give me 2O2 gas and 2NO2 gas. Okay, so what's amazing about mechanisms, it's amazing development of human thinking, is that we can imagine that we're figuring out what's actually happening with these molecules. We're not just looking at what the reactants are and what the products are. We're figuring out what's happening over time. Over time, these are colliding and making these intermediates. These intermediates are then reacting with other reactants and they're disappearing. They're not in the product, but we know. So what you can do is you can use light, you can shine in light and study it while the reaction is occurring to see if those intermediates exist, okay? So our intermediates are, yes, they're definitely our intermediates. They're O and they're NO3, right? The ones that are formed in an earlier step and then used up in a later step, those are called intermediates, okay? So there's that problem. Good. Okay, so I kind of got a little bit ahead there, but that's good because that's going to make these a lot easier for you. So this problem, what it says here is you want to write the rate law again of an elementary step. Remember, we can't write the rate law for an overall reaction just by looking at the balanced equation. You can't do that, but you can do it for an elementary step. So write the rate law for the following elementary reaction. This is ethyl bromide reacting with hydroxide. This is one of the few I've seen in the problems here where it's actually in water. It's dissolved in water. It's an aqueous reaction. So ethyl bromide plus hydroxide forms ethanol plus the bromide ion. Use K1 to stand for the rate constant. These are very easy. So all you got to do is just write out. It's okay. So I'm going to start by showing you the equation. So CH3 CH2Br aqueous plus OH minus goes to CH3CH2OH. You're making an alcohol out of a bromide. That's kind of cool. An alkyl halide it's called. Okay. So all you got to do is we're just going to worry about, this is elementary, so we could just use the coefficients. They're both 1. So rate equals K1. They say to use K1 times concentration CH3 CH2Br, and that's a 1, so just leave it like it is, times concentration of OH minus. Okay, and there's your rate. There is your rate law. I'm sorry, not your rate law, right? Okay, so we've come a long ways in this chapter. We've done a lot, right? It's an intense chapter, but it's really helpful for those of you going on into organic chemistry, okay? So there's that type of problem. There's one more, which is a little more complicated. In this one, you're going to write the rate law for a mechanism, not for just an elementary step, for the whole mechanism. We're just going to do 2 steps. We're not going to do 3 steps in here. It gets complicated. So this is writing the rate law implied by a simple mechanism. So remember, the mechanism is the combination of steps. Each one's an elementary step or an elementary reaction. Each has its own rate constant. To combine together is the overall reaction. And then the whole thing together is also the mechanism. This is telling us what's actually happening at the molecular level. So they give us these 2. They also tell you that K1 is much less than K2. That's telling you slow, fast, right? Let me show you what I mean by that. Rate is proportional to the rate constant, right? Rate equals K times the concentration of whatever the reactants are. If K is large, rate is large. Meaning if K is large, it's a fast reaction, okay? So what we have in chemistry are kind of 2 possibilities. One is the first one is slow and the second one is fast. Or the reverse of that. The first one is fast and the second one is slow, okay? Now, the terminology we often use is what's called rate limiting or rate determining. If something is slow, if a step is slow, it's called rate limiting. It limits how fast the rate can be because it's slow. So an analogy would be that you're on the highway driving a car and you go miles really fast. There's no traffic, so you're going 100 miles an hour. And then suddenly you hit traffic. That last mile might have so much traffic that you're only going 1 mile an hour. So you could go 100 for a long time and then do 1 mile. And then overall, that second part is going to be rate limiting. It's going to be rate determining. The amount of time you spent on the road is actually mostly determined by the slow step because it takes more time. So in this case, it's saying K1 is much less than K2, meaning it's slow. Okay, that's sometimes hard for people to recognize. The smaller K is, the slower it is, the more it's the rate determining step. So there are 2 possibilities again. One is that K is slow, one is that K2 is slow. You're comparing the 2. If they're equal, that complicates things. But usually in chemistry, strangely enough, one is usually much larger than the other. 1K is much larger. It's very rare they're the same. It could happen, but it's rare that that happens. Okay, because usually one step involves breaking bonds and another step involves forming bonds. Breaking bonds requires energy, it's slow. forming bonds, forms energy, it's fast. So usually you do have one fast, one slow, or one slow, one fast, okay? So what they want you to do is to write the overall equation. We know how to do that. You just combine those together. But they want you to write the rate law for the, essentially the rate limiting step, the rate determining step. Is that what they say? Write the experimentally observable rate law for the overall, okay? Should not contain concentrations of any intermediates. Okay, that's a little issue there. Now, the first one that pops up here is actually the easier one. One is harder than the other. And when you do this, you might get the harder one first and then do an easier one. But in this case, it came up easier first. So when K1 is much less than K2, that means it's the rate determining step. If that happens, then all you got to do is write the rate law for that step, and that's the rate law for the experimentally observable experiment, right? So if the first one is slow, just write out the rate law for the first step, and that'll be the rate law for the overall. If K2 is much smaller than K1, or K1 is much larger than K2, then it's a little more involved. So let me show you this one first, and then we'll look at an example where it's a little more, where K2 is smaller. And again, it's because it's two steps, it's almost like this. Imagine, I used to give this analogy in lecture. Imagine that you're pouring sand through a cylinder and you got like one opening, but it's a big opening. So you're just pouring sand through here. If that opening is large, it's going to go real fast. So it might only take half a second. But then if I have this, like, it narrows down here to a tiny little hole, that's like an hourglass, right? We used to use those for timers. They're cool, right? This is the rate determining step. It's going to go real slow through here. So if you say, oh, how long did it take for all the sand up here to get down here? This was fast. We can ignore this step. That only took a second. But this might take a minute or 10 minutes. So this is what we determine, okay? If it happens in the second step, it's more complicated than if it happens in the first step, okay? So let me show you this problem, and then we'll look at another example where we might have K2 is much smaller, okay? So in step one, we have 2NO goes to N2O2, and they say there's a K1 for that. So first step, write the overall balanced equation. So I'm going to write these both down first. By the way, the ones that we see in here are famous because they were done like in the 40s and 50s, and they've been in textbooks for a long time now, for like 40 years. Okay. So now, again, I'm going to note K1 is much less than K2. So K1 is slower. Smaller means slower. Rate determining. Or rate limiting. Okay. If that's the case, let's do the overall. Is there anything we can cancel? Yes. So you get 2NO goes to, I'm sorry, plus O2. This is a reactant. My apologies. Goes to 2NO2. Okay. Now, we don't know what the rate law is from the overall. Remember, I said that earlier, we can't tell what it is for the overall. You have to do it from our analysis of the mechanism. So here's what happens. If the first step, so if step one is much less than step two, I'm really saying if K1 is much less than K2, then you can just ignore step two and just look at step one. This rate, R1, will be K1 times NO bimolecular, right? There's a 2 there. This is the rate law for the experiment. If you actually did, went through the whole thing here, what you would find is that the overall rate law would be K1 times NO squared, concentration of NO squared, okay? And that would be it, okay? Now there is a rate law for the second step. Oops, sorry. N2O2 times O2. Okay, but what happens is that process is so fast that it doesn't really affect the overall rate. And here's what I mean. Suppose this takes, I'm saying this is slower, suppose this takes an hour and this takes 1 second. How long was the overall? The overall speed, the overall, amount of time that it takes for this reaction to occur would be an hour plus a second. It's an hour. This is what's determining how fast it's going, right? If I make this even 2 seconds, it still doesn't matter. Overall, it's taking an hour. Okay, so that's why it says much less than. It's a big difference. We're not talking like 1 hour versus an hour and a minute. It's going to be like 10 or 100 times difference in time. Okay, so that's your case one. I'll call this case one. K1 is much less than K2. Okay, then it's easy. You just look at the first one. Okay, the second possibility is more difficult, and that's where K2 is much less than K1. So let me see if I can find that. Oh. Actually, I'm looking through here. It looks like every one of them is K2 is much larger. Oh. None of them are K2 is much smaller. That's sort of strange. Did I pick that on purpose? Yeah. Okay. It is possible. Let me just check something. 10.5. Mechanisms. Let's see. Trying to see if I can find out when it's like that. Okay, I found one. I'm right. So it turns out I didn't assign this to you. I didn't put it in the Alex for your assignment, but I'm going to show it to you anyways. You're not going to have to do this, but just for my own kind of self-consciousness of, for those of you that are going to organic chemistry, I want you to see this. Okay, so you won't have to do this on your homework, but I want to show it to you. So in this particular example here, it's the same idea. You have two equations, but K2 is much smaller than K1. So how do we deal with that, right? Okay, so this is case 2. So here's our two equations. We're going to do the same thing, balance the equation, figure out the rate law. Now, in order to solve this one, okay, so let me write this down. So step 1, NO plus O2 goes to NO2 plus O, and then there's a K1. Step 2, NO plus O goes to NO2. Step 2, K2, right? What I'm going to do is I'm going to write down the rate law for each step. Right? These are elementary steps, okay? So what we can do is we can write the overall equation, right? The overall equation, it looks like the O is going to cancel. And that's an intermediate, right? So you're going to have NO So overall, you're going to have NO, two of them, right? 1, 2, plus O2. Of course, they're gases. Goes to 2NO2. Okay. But now K1 is much greater than K2. That's what's different about this one right here. So now this is case 2, a little bit more complicated. Okay. Here's what's happening. This is the slow step, right? K2 is smaller, so this is the rate determining step. So actually the rate is just going to be K2 times NO times O. That would actually be the overall rate law, but there's a problem with that. It has an intermediate, which is the O. See how that's an intermediate? We didn't put that in. The way this actually works is, the overall equation is we're putting in NO, we're putting in O2, and we're getting NO2. We're not adding any O. It's getting formed in this intermediate step. So it's considered very poor form and unacceptable to write the rate law involving an intermediate, because an intermediate is not really observed as a reactant or a product. We have to do it as a reactant or a product. So here's what we do. We take the reaction that has the intermediate here. Oh, yeah, right, here we go. Okay, so what I'm going to do is I'm going to say concentration of O, and then concentration of NO here. I'm going to write, let's see, where is it? Oh, here we go. I'm going to do this. I'm going to take the first step, and I'm going to say we have what's called rapid equilibrium, which is a topic from the next chapter, which is actually why I didn't make this an assigned problem. What you're going to do is you're going to write this equation a little differently. This is called rapid equilibrium. Okay, and this is going to be called K1, and this is going to be called K minus 1. What I'm claiming now is that for this fast step, what happens is very quickly, this is happening fast. So these two are going to form these products really fast. But then over time, what will happen is these will start reforming the reactants. So it goes back and forth. Both processes occurring simultaneously. That's called fast equilibrium. And so when you're in fast equilibrium, R1, meaning the forward reaction forming products, is equal to R minus 1, which means it's equal to the reverse reaction, sometimes called forward reverse, which means K1 times NO times O2 is equal to K minus 1 times NO times O. And that equation has O in it, which is the intermediate that we don't want to have in our overall equation here, in our rate determining step. So what you do is you just do a little algebra. You solve for O. So you divide both sides by K minus 1. And you divide both sides by NO. Cancel, cancel. And now you've got O. And so O, concentration of O, is equal to K1 over K minus 1 times NO over NO times O2. This cancels. So concentration of O is just equal to K1 over K minus 1, which is another constant. So I'm just going to call it K, I'll call it KEQ for equilibrium, times concentration of O2. So now it's in the form of a constant and a concentration of O2, which is a reactant. So I can substitute this into our rate determining step. It's going to be K equilibrium times K2 times NO times O2. Okay, so I just substituted in here these two right there. Now KEQ times K2, well, it's just a new K, so I'll call it K3. You can just make up any subscript you want, times NO times O2. So there's your experimental rate law. So see, it's a little bit more complicated, right? The tricky part is you just go ahead and you write out each step, write the rate law for each step, The second step is slow, so that's the rate law. That's going to be the rate determining step. That's the one you're going to look for. It's just you have to get rid of the intermediate. You can't have the intermediate in there. So you come back to the first step and do this fast equilibrium. So K1 times these concentrations equals K minus 1 times these concentrations, the products. So reactants and products. Set them equal to each other. Do the algebra to get that intermediate all by itself. You know, any K's, like I have K1 times K2 times K3, it's just some K, right? You just, you know, K4 if you want to call it that, okay? When you look at the, well, you won't see this question, but in the question, they actually just say, you know, K minus 1 is the reverse, K minus 2 is the reverse of the second one, okay? So again, you don't have to do that one, it's a more complicated one, but I wanted to show it to you because that is a general standard type problem that you might see if you were doing this out of a textbook or if you were doing it in a general chemistry, in an organic chemistry class, okay? So there you go, so there's our last section. Take care.